In this lesson, we're going to look at a kind of nice little example of how our understanding of conservation of angular momentum and rotational inertia can be used to completely understand that dramatic effect when an ice skater at the end of the routine spins slowly with their arms, set themselves into a spin somewhat slowly with their arms outward, and then they dramatically pull their arms in and spin faster and end their routine. Well, we can absolutely understand that in terms of the physics we now know based on conservation of angular momentum. So if the ice skater puts herself into a spin, and for our analysis, we're assuming that there's no friction in the problem. So as it says here, no friction. Theoretically, she will spin forever. No air resistance, no friction between her skates and the ice. That means there are no external torques to stop her from spinning. So dLdt is zero, angular momentum is constant. Also, to simplify our analysis, we're going to assume her axis of rotation is directly down the center of her body, which it would be whether we do this approximation or not. But to make the moment of inertia calculation easier so we don't have to look at the moment of inertia of an actual skater's body, we're going to assume that our skater is all hands. So in this case, she has big, massive hands at a distance r from the axis about which she's spinning. So the initial angular momentum that we're looking at when she sets herself into a spin, again, somewhat slowly because we're going to see a dramatic effect, is based on L initial equals her initial moment of inertia times her spin velocity omega initial. Well, she pulls her arms in dramatically to end her routine. So our final condition, she pulls her arms in dramatically. Her R is now R on 2. She reduces her moment of inertia, and if I is made smaller, omega has to proportionally become larger. So let's figure out how much smaller I becomes. Well, she starts out with her moment of inertia being dominated by her two big bulbous hands and has 2 mr squareds dominating her rotational inertia. So we're assuming everything else about her is super light except those big bulbous hands. And when she pulls them in to a radius of r on 2, look at the algebra we get. So we have, in the first case, 2mr squared remains 2mr squared. But now we have 2mr on 2 squared, so the squared on the bottom becomes a 4. 2 divided by 4 is 1/2, so we get 1/2 mr squared when she pulls her arms in. And as it says here, please make sure you get this in your notes, that if the moment of inertia is 4 times smaller when she pulls her arms in, that means omega final must get 4 times larger to keep L initial equals L final. Now the last little bit of this problem, and this problem is often in a multiple choice type of format for the AP test if they decide to ask the skater spinning problem. How about energy? Is energy conserved? Well, we can see here, spoiler alert, it is not, but let's see why not. If her final moment of inertia is 1/4 the initial moment of inertia, as we have here, and her final velocity then is 4 times her initial velocity, we're just going to use those values and substitute them in to the kinetic energy final 1/2 I omega squared, where we can see we use the 1/4 I initial in here for the I final, and we use the 4 omega initial for the final velocity. And when we do the algebra, we get 4 1/2 I initial omega. Actually, there should be an omega initial in there, omega initial squared. So we get 4 times the initial kinetic energy, And really the question for a multiple choice question would be where does the energy come from? It can only come from one place. There's no external torques or external anything going on. So that energy comes from the energy it takes her to move her arms in. Pulling her arms in doesn't happen without energy. And the energy that she uses to pull her arms in is seen as an increase in the kinetic energy of the system. So there we have a nice little short lesson, but one that is often seen if you watch any figure skating. You see the same thing for divers when they spin, they tuck in, get real tight, reduce that moment of inertia. So let me erase my ink here. So anytime the moment of inertia is reduced, the omega final becomes bigger, whether it's a skater or diver, or dancers as well. And now we can understand how that happens based on angular momentum.